Everything around you seems solid and predictable. The chair beneath you, the air you breathe, even your own body appears to obey simple rules. But beneath that familiar world lies a reality unlike anything you have ever imagined. For centuries, people believed that if they looked closely enough, they would eventually discover the smallest building block of nature. It sounded like a simple question with a simple answer. Ancient philosophers called these tiny building blocks atoms, a word meaning indivisible. They imagined particles so small that nothing could ever be broken into anything smaller. For thousands of years, no one could prove whether atoms truly existed. They remained little more than clever ideas, invisible to every eye and beyond the reach of every instrument. Then science began revealing a hidden universe. Experiments showed that matter was not continuous at all. Everything around us was built from unimaginably tiny particles. As microscopes improved and technology advanced, scientists uncovered a world that no human had ever seen before, a world where ordinary experience no longer applied. Inside every grain of sand, every drop of water, and every cell of your body exists a universe of restless particles moving with astonishing speed. At first, scientists expected these tiny particles to behave like miniature versions of everyday objects, following the same predictable rules that govern falling apples and orbiting planets. Instead, they found something completely unexpected. The smallest particles in nature refused to obey common sense, challenging every assumption about how reality should work. Electrons did not move like tiny planets around a miniature sun. Light refused to behave as only a wave or only a particle. Nature seemed to ignore the rules everyone trusted. The deeper scientists looked into the microscopic world, the stranger everything became. Familiar ideas about position, motion, and certainty began slipping away. Objects appeared capable of behaving like waves. Waves sometimes behave like particles. The line separating the two seemed to disappear completely. Events that looked impossible in everyday life became perfectly normal inside the quantum world. Reality itself appeared to follow an entirely different set of rules. Many of the greatest scientists in history struggled to accept these discoveries. Some believed the experiments were flawed. Others wondered whether nature was hiding something even deeper. Yet every new experiment confirmed the same astonishing conclusion. The universe at its smallest scale behaves in ways that no one had predicted. By the end of the 19th century, scientists believed they had nearly completed their understanding of nature. The laws of physics seemed elegant, predictable, and almost perfectly complete. Newton's laws explained motion with astonishing accuracy. Maxwell's equations described electricity, magnetism, and light so successfully that many believed no great mysteries remained. Yet hidden behind this confidence was a small problem that refused to disappear. It seemed insignificant at first, but it would soon challenge the foundations of physics itself. The mystery involves something so ordinary that everyone experiences it every day: heat. Every warm object, from glowing metal to distant stars, continuously radiates energy. Scientists wanted to understand exactly how hot objects produce light. The mathematics appeared straightforward, but every calculation led to an impossible conclusion. According to classical physics, a hot object should emit an infinite amount of energy at very short wavelengths. This absurd prediction became known as the ultraviolet catastrophe. The theory suggested that even a simple glowing piece of metal should release limitless energy, something no experiment had ever observed. Nature clearly disagreed with the equations. Every laboratory measurement showed that the energy remained finite, no matter how carefully scientists repeated the experiments. For years, researchers searched for mistakes in their calculations. Yet every attempt produced the same contradiction between theory and reality. Then in 1900, a German physicist named Max Planck proposed an idea that even he found difficult to believe. Instead of assuming that energy flowed continuously, Planck suggested something revolutionary. Perhaps energy could only be emitted or absorbed in tiny, indivisible packets. He called these tiny packets quanta. It was a simple mathematical assumption, introduced only to make the equations match the experiments. To Planck's surprise, the impossible problem disappeared. His new equations matched the laboratory results with remarkable precision. At first, Planck believed the idea of energy quanta was merely a useful mathematical trick rather than a description of physical reality. But nature had something far more extraordinary in store. What began as a mathematical shortcut would soon become the foundation of an entirely new branch of science. A few years later, a young physicist named Albert Einstein took Planck's strange idea one step further, making a prediction that shocked the scientific community. Einstein proposed that light itself is made of tiny packets of energy, later called photons. This meant light could behave as individual particles as well as waves. The idea sounded outrageous. For decades, experiments had shown that light behaved beautifully as a wave. How could it suddenly also behave like particles? Yet experiment after experiment confirmed Einstein's prediction. The impossible slowly became undeniable, and the first door into the quantum world had finally opened. With Planck's quanta and Einstein's photons, classical physics could no longer explain everything. Humanity had unknowingly stepped into a universe governed by rules unlike any it had ever imagined. Some experiments answer questions, others create mysteries so profound that they reshape the future of science. The double-slit experiment belongs to the second kind. At first glance, the experiment appears almost too simple to matter. A light source, a barrier with two narrow slits, and a screen placed behind it. The goal seems straightforward. Shine light through the two openings and observe the pattern that appears on the screen beyond the barrier. If light behaves like tiny particles, each particle should pass through one slit or the other, creating two bright bands directly behind the openings. But when scientists performed the experiment, something completely unexpected appeared. Instead of two bright bands, the screen displayed a beautiful pattern of alternating light and dark stripes. This pattern is known as an interference pattern. It is exactly what waves produce when they overlap, strengthening each other in some places and canceling each other in others. The results suggested that light was not behaving like individual particles at all. It behaved exactly like a wave spreading through both slits simultaneously. At first, this seemed like the final answer. Light was simply a wave, and the mystery appeared solved. But nature had another surprise waiting. Scientists decided to make the experiment even more precise. Instead of sending a continuous beam of light, they fired one photon at a time. Surely a single photon could only travel through one slit. There were no neighboring photons to create overlapping waves. Yet something astonishing happened. Even when photons were fired individually, they slowly built the very same interference pattern on the screen. It was as though each photon somehow interfered with itself, behaving like a wave while still arriving as a single particle. The mystery deepened further when scientists placed detectors beside the slits to discover which opening each photon actually passed through. The moment they measured the photon's path, the interference pattern disappeared completely. The photons suddenly behaved like ordinary particles. Nothing else in the experiment had changed. The only difference was that someone had attempted to observe which slit the photon used. It seemed as though the act of measurement itself had changed the outcome. A conclusion so strange that even the world's greatest physicists struggled to accept it. Did the photon travel through one slit, both slits, or neither in the ordinary sense? Quantum mechanics refused to offer an answer that matched everyday intuition. The double-slit experiment became one of the most famous experiments in scientific history because it challenged the very meaning of observation and reality. More than a century later, every improved version of the experiment continues producing the same astonishing results, confirming that the quantum world does not behave like the world we experience every day. The deeper scientists explored this remarkable experiment, the more they realized that certainty itself might be an illusion, opening the door to one of quantum physics' most revolutionary ideas. By now, scientists understood that the quantum world followed unfamiliar rules. Yet the deeper they explored, the stranger those rules became, challenging every idea that once seemed certain. In everyday life, objects behave predictably. A baseball follows a clear path through the air, and a rolling ball always has a definite position and speed at every moment. Tiny quantum particles refuse to behave this way. They cannot always be described as following a single, well-defined path through space. Instead, their behavior is described by probabilities. Rather than predicting exactly where a particle will be, quantum physics predicts where it is most likely to be found. Imagine watching a swarm of fireflies on a dark summer night. You cannot predict the exact path of each one, but you can estimate where the group is most likely to appear. Quantum particles behave in a surprisingly similar way. They are described by a probability distribution rather than a precise trajectory through space. This does not mean scientists lack accurate instruments. Even with perfect equipment, nature itself appears to behave probabilistically at its smallest scales. Before a measurement is made, a particle does not seem to possess one definite location in the way everyday objects do. Instead, many possibilities coexist. Physicists describe these possibilities using something called a wave function. It contains every possible outcome that a measurement might reveal. The wave function does not tell us what definitely exists. Instead, it provides the probabilities of what may be observed when an experiment takes place. For many scientists, this idea was deeply unsettling. Classical physics promised certainty, while quantum mechanics seemed to replace certainty with probability. Albert Einstein admired quantum theory's success, but struggled to accept its strange implications. He famously believed that nature should never depend on pure chance. He expressed his doubts with one unforgettable statement: "God does not play dice with the universe." It became one of the most famous quotes in scientific history. Others disagreed completely. Physicists like Niels Bohr argued that probability was not a weakness of quantum theory, but one of nature's most fundamental characteristics. Bohr believed the quantum world simply operates differently from the world of everyday experience. Accepting that difference was essential to understanding reality. This disagreement sparked one of the greatest scientific debates ever recorded. Two brilliant minds defended completely different visions of how the universe truly works. For decades, experiments repeatedly favored the predictions of quantum mechanics. Again and again, nature behaved exactly as the strange theory predicted. Modern technologies such as lasers, semiconductors, and magnetic resonance imaging all rely upon these remarkable quantum behaviors every single day. Although the quantum world appears mysterious, its predictions have become some of the most accurate in the entire history of science. Yet an even stranger mystery was waiting ahead. If particles are described only by probabilities before measurement, what exactly happens at the instant an observation is finally made? The more scientists explored the quantum world, the more they realized that nature was protecting one of its deepest secrets. Some things could never be known with perfect certainty. In 1927, a young German physicist named Werner Heisenberg introduced an idea that would forever change the way scientists understood measurement and reality. His discovery became known as the uncertainty principle. Despite its name, it was not about faulty instruments or human mistakes. It described a fundamental property of nature itself. Imagine trying to photograph the wings of a hummingbird in complete darkness. To see them clearly, you must shine a bright light, but the light itself disturbs what you are observing. At the quantum scale, every attempt to observe a tiny particle affects that particle in some way. Observation is no longer passive. It becomes part of the experiment itself. The smaller the particle, the greater this effect becomes. Measuring one property with extreme precision makes another property less certain at exactly the same time. The most famous example involves position and momentum. The more accurately you determine where a particle is, the less accurately you can know how it is moving. Likewise, if you measure a particle's momentum with extraordinary precision, its exact position becomes increasingly uncertain. Nature refuses to reveal both perfectly at once. This was not a limitation of technology. Even a perfect measuring device could never overcome this fundamental boundary built into the universe. For many scientists, this idea seemed unbelievable. Surely every particle must possess an exact position and an exact momentum, even if humans cannot measure them. But every experiment pointed toward the same conclusion. The uncertainty was not hiding inside the equipment. It was woven into the fabric of quantum reality itself. Heisenberg's principle forced physicists to abandon the dream of perfect prediction. At the smallest scales, certainty gives way to probability. This does not mean that quantum physics is random or chaotic. Its equations predict outcomes with extraordinary accuracy, but only in terms of probabilities rather than certainties. Imagine standing before a thick morning fog. You know a ship is somewhere beyond the mist, but you cannot identify its exact position until the fog begins to clear. Quantum particles behave in a surprisingly similar way. Before measurement, they are described by a range of possibilities rather than one perfectly defined reality. Albert Einstein found this deeply unsettling. He believed the universe should follow hidden laws that preserve certainty, even if those laws had not yet been discovered. Niels Bohr disagreed completely. He argued that uncertainty is not a flaw in quantum mechanics, but one of nature's most fundamental truths. Their debate became legendary, inspiring decades of experiments designed to test whether certainty or probability truly governs the microscopic universe. Time after time, nature sided with quantum mechanics. Every new experiment strengthened confidence that uncertainty is not ignorance, but an essential feature of reality itself. The uncertainty principle revealed that the quantum world cannot always answer every question we ask. Instead, it invites us to think differently about what it truly means to know something at all. Imagine flipping a coin into the air. While it spins, you know it will eventually land as either heads or tails. In everyday life, only one outcome can ever become real. The quantum world tells a very different story. Before a measurement is made, a particle does not always appear to exist in just one definite state. Instead, it can exist in what physicists call a superposition, a combination of multiple possible states existing simultaneously until an observation takes place. This idea is not a matter of imagination or philosophy. It emerges naturally from the mathematics of quantum mechanics and has been confirmed through countless experiments. Imagine listening to a beautiful chord played on a piano. Several notes exist together, creating one harmonious sound rather than replacing one another. Quantum superposition is similar in spirit. Multiple possibilities coexist within a single quantum system, each contributing to the system's overall behavior. An electron, for example, can exist in several possible energy states described by one wave function instead of occupying only one definite state. Only when a measurement is performed does one specific outcome appear, while every other possibility seems to disappear from observation. This strange behavior puzzled scientists from the very beginning. How can something exist in multiple possible states without choosing just one? Classical physics offers no satisfying answer because nothing in our everyday experience behaves this way. Superposition belongs entirely to the quantum world. Experiments with electrons, photons, and even larger particles repeatedly demonstrate the same astonishing result. Superposition is not a theoretical curiosity, it is a measurable reality. Researchers have even created superposition in carefully controlled atoms and molecules, proving that the phenomenon extends beyond individual particles. The challenge is that superposition is extremely fragile. The slightest interaction with the surrounding environment can destroy it almost instantly. This process is known as decoherence. As quantum systems interact with the outside world, the delicate superposition rapidly disappears, leaving only ordinary classical behavior. That is why we never see everyday objects existing in obvious superpositions. Billions of interactions with their surroundings erase those quantum effects almost immediately. Yet inside laboratories, scientists have learned to isolate tiny systems well enough to preserve superposition for surprisingly long periods of time. These remarkable experiments have opened the door to revolutionary technologies, including quantum sensors, quantum communication, and the rapidly advancing field of quantum computing. Instead of processing information as simple zeros or ones, quantum computers exploit superposition to explore many possible solutions at the same time. Although building practical quantum computers remains an enormous challenge, early machines have already demonstrated capabilities impossible for ordinary computers to imitate. Superposition teaches us one of the deepest lessons in modern science. Reality at its smallest scales is not limited by everyday intuition, and the universe is far richer than appearances suggest. By the 1930s, quantum mechanics had become one of the most successful theories in science. Yet many physicists were deeply uncomfortable with what it seemed to say about reality. If quantum particles could exist in multiple states at once, a troubling question naturally followed. Could the same strange behavior also apply to larger objects? In 1935, the Austrian physicist Erwin Schrödinger proposed a remarkable thought experiment. He never intended it to describe reality, but to expose how strange quantum theory appeared. Imagine placing a cat inside a sealed box where no one can see what is happening. The cat's fate depends entirely on a single quantum event. Inside the box is a tiny radioactive atom. Quantum mechanics says that during a certain period, the atom has a specific probability of decaying or remaining unchanged. If the atom decays, it activates a detector connected to a small vial of poison. The vial breaks, releasing the poison and causing the cat to die. If the atom does not decay, nothing happens. The poison remains sealed, and the cat continues living safely inside the closed box. Before anyone opens the box, quantum mechanics describes the atom as existing in a superposition of both decayed and undecayed states. If the atom exists in both possibilities simultaneously, what does that imply about everything connected to it, including the unfortunate cat? According to the mathematics, the entire system appears to exist in a superposition. The cat is described as both alive and dead until an observation is made. This conclusion sounds absurd because it clashes completely with everyday experience. Cats are either alive or dead. They are never both at the same time. Schrödinger created this paradox to challenge the interpretation of quantum mechanics, not to suggest that real cats actually exist in such bizarre conditions. The experiment quickly became one of the most famous thought experiments in scientific history, sparking debates that continue to this very day. Some physicists argue that the wave function collapses the moment a measurement occurs, selecting one definite outcome from many possibilities. Others believe every possible outcome continues to exist, giving rise to the many worlds interpretation, where countless parallel realities branch apart with every quantum event. Another interpretation suggests that interactions with the surrounding environment gradually destroy superposition through a process known as decoherence. Despite decades of research, no single interpretation has gained universal acceptance. The mathematics works beautifully, yet its deeper meaning remains uncertain. Modern experiments have created quantum superpositions involving increasingly larger molecules, pushing the strange boundary between the quantum world and everyday reality. Schrödinger's cat reminds us that quantum mechanics is not merely a collection of equations. It forces us to confront profound questions about observation, reality, and the very nature of existence itself. Imagine creating two particles that share a mysterious connection. No matter how far apart they travel, measuring one appears to influence the other instantly. At first, this idea sounds impossible. Nothing should communicate faster than light, according to Einstein's theory of relativity. Yet quantum mechanics seem to suggest something extraordinary. This strange phenomenon is known as quantum entanglement. It is one of the most remarkable and puzzling discoveries ever made in modern physics. When two particles become entangled, they no longer behave as completely independent objects. Instead, they form a single quantum system, even when separated by enormous distances. Imagine owning a pair of magical coins. No matter how far apart they are, the moment one lands on heads, the other instantly lands on tails. Quantum entanglement is not exactly like magical coins, but the analogy captures the surprising idea that distant particles can display perfectly correlated behavior. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen challenged quantum mechanics with a famous argument now known as the EPR paradox. Einstein believed that something must be missing from quantum theory. He suspected that hidden variables secretly determined the outcomes long before any measurement occurred. He disliked the idea that nature could produce instant correlations across vast distances. He famously called the phenomenon spooky action at a distance. For decades, scientists debated whether Einstein was correct or whether quantum mechanics truly described reality as strange as it appeared. Then in 1964, physicist John Bell proposed a brilliant mathematical test capable of settling the argument through carefully designed experiments. Bell's theorem showed that if hidden variables controlled reality, certain statistical patterns should always appear in experimental results. Quantum mechanics predicted different patterns. For the first time, scientists had a practical way to compare Einstein's intuition with quantum theory. Beginning in the 1970s and continuing through the decades that followed, increasingly precise experiments tested Bell's predictions with extraordinary accuracy. Again and again, nature agreed with quantum mechanics. The experimental results consistently violated Bell's inequalities, ruling out many hidden variable explanations. These discoveries did not prove that information travels faster than light. Instead, they revealed that quantum particles share correlations unlike anything found in classical physics. Today, quantum entanglement has moved beyond theory into practical technology. Researchers routinely create entangled photons, electrons, and even larger quantum systems inside laboratories. Entanglement now forms the foundation of quantum communication, quantum cryptography, and future quantum networks capable of unprecedented levels of security. Scientists are also developing the quantum internet, where entanglement may one day connect distant quantum computers across entire continents. More than a century after quantum theory was born, entanglement remains one of its greatest mysteries, reminding us that the universe is connected in ways far stranger than human intuition ever imagined. For more than half a century, ordinary computers have transformed civilization. They calculate, communicate, and solve problems at astonishing speeds, yet they still face limits that cannot easily be overcome. Every digital computer, from the smallest smartphone to the largest supercomputer, processes information using tiny units called bits. Each bit can exist in only one of two states, 0 or 1. This simple system has powered the digital revolution. Billions of calculations are performed every second by combining enormous numbers of these binary bits together. For most everyday tasks, this approach works beautifully. But some scientific problems are so complex that even the world's fastest supercomputers would need millions of years to solve them. Nature, however, already performs calculations using the strange rules of quantum mechanics. Scientists began wondering if computers could do the same. The answer led to one of the most exciting technologies of the 21st century, the quantum computer, a machine designed to harness the bizarre behavior of the quantum world. Instead of ordinary bits, quantum computers use quantum bits, better known as qubits. Unlike classical bits, qubits are not limited to being only 0 or only 1. Thanks to quantum superposition, a qubit can represent multiple possibilities simultaneously until it is measured, dramatically expanding the ways information can be processed. When several qubits become entangled, they begin working together in ways impossible for ordinary computers, creating an entirely new style of computation. Rather than checking one possible solution after another, a quantum computer can explore many possibilities at the same time, making certain calculations dramatically more efficient. This does not mean quantum computers are faster at everything. For many everyday tasks, traditional computers remain the better choice. Their true power appears when solving highly specialized problems involving enormous numbers of possibilities, such as molecular simulations, optimization, and advanced cryptography. One promising application is medicine. Quantum computers may eventually simulate complex molecules with extraordinary precision, helping scientists discover new drugs much faster. Another exciting field is materials science. Researchers hope quantum simulations will lead to stronger materials, cleaner energy technologies, and more efficient batteries. Artificial intelligence may also benefit from quantum computing. Some researchers believe future quantum algorithms could accelerate certain forms of machine learning. Building these remarkable machines is extraordinarily difficult. Qubits are incredibly sensitive and can lose their quantum behavior through the slightest interaction with their surroundings. To protect them, many quantum computers operate inside sophisticated cryogenic systems, cooled to temperatures colder than outer space, reducing unwanted disturbances. Today, companies and research laboratories around the world are racing to build larger, more stable quantum computers capable of solving practical real-world problems. Although the technology remains in its early stages, many experts believe quantum computing could become one of the greatest technological revolutions since the invention of the digital computer. Quantum computers remind us that the strangest ideas in physics often become tomorrow's greatest innovations, proving once again that understanding nature can transform the future of humanity. One of the most unsettling questions in quantum physics has nothing to do with complicated mathematics. Instead, it asks something far more personal. What is reality when nobody's looking? For centuries, people assumed the universe existed exactly as it appeared. Mountains stood where they stood. Planets followed their paths, and every object possessed definite properties at every moment. Quantum mechanics challenge this comforting picture. At the microscopic level, particles seem to exist as probabilities until a measurement finally reveals a specific outcome. This strange idea led many people to wonder whether observation somehow creates reality itself. The question quickly spread far beyond physics into philosophy and popular culture. It is important to understand what physicists actually mean by an observation. It does not necessarily require a human being watching with their eyes. In quantum mechanics, an observation is any interaction that forces a quantum system to exchange information with its surroundings, producing a measurable outcome. A photon striking a detector, an electron colliding with an atom, or a particle interacting with its environment can all serve as observations in this scientific sense. This means the universe does not wait for conscious humans before events occur. Quantum systems constantly interact with other particles throughout the cosmos. Even so, the mathematical description before measurement remains deeply mysterious. The wave function contains many possible outcomes, yet only one is ultimately observed. What causes that transition remains one of the greatest unanswered questions in modern physics. Scientists still debate whether the wave function truly collapses or only appears to. The Copenhagen interpretation suggests that the wave function collapses during measurement, leaving a single outcome while every other possibility disappears. The many-worlds interpretation proposes something far more astonishing. Every possible outcome continues to exist, each unfolding within its own branching universe. According to this view, reality continuously divides into countless parallel histories, each containing a different version of events unfolding simultaneously. Other interpretations suggest that unknown physical processes or hidden mechanisms determine the outcome without requiring multiple universes or mysterious collapses. Despite decades of debate, every interpretation makes the same experimental predictions. Nature has not yet revealed which explanation, if any, truly reflects reality. Modern experiments continue pushing these questions further by controlling quantum systems with extraordinary precision and testing the limits of observation itself. Researchers have demonstrated quantum behavior in increasingly larger objects, blurring the boundary between the microscopic world and the familiar everyday world. Each experiment confirms the extraordinary accuracy of quantum mechanics, while leaving its deeper meaning just beyond our complete understanding. Perhaps the greatest lesson is one of humility. The universe does not always behave according to human intuition, and reality may be far richer than our senses can reveal. Quantum physics reminds us that science is not merely about collecting answers. It is about asking better questions, following the evidence, and remaining open to truths that once seemed impossible. More than a century has passed since quantum theory was born, yet its journey is only beginning. Every year, new discoveries reveal that the quantum world is even stranger than scientists once believed. What began as an attempt to explain the behavior of light has grown into one of the most successful scientific theories ever developed, transforming both science and technology. Today, quantum mechanics forms the foundation of modern electronics. Every smartphone, computer, laser, and semiconductor chip depends on principles discovered in the quantum world. Without quantum physics, there would be no transistors, no microprocessors, no MRI scanners, no LEDs, and no internet as we know it today. Yet these achievements may be only the first chapter. Researchers believe the greatest quantum revolution is still waiting in the future. Around the world, scientists are building increasingly powerful quantum computers capable of solving problems beyond the reach of even the fastest supercomputers. Quantum communication networks promise virtually unbreakable encryption, protecting information with the fundamental laws of physics rather than mathematical complexity. Engineers are developing quantum sensors so sensitive that they may detect underground structures, hidden minerals, earthquakes, and even subtle changes in Earth's gravity. Astronomers are using quantum technologies to build more accurate telescopes, allowing humanity to explore distant galaxies with greater precision than ever before. Medical researchers hope quantum simulations will accelerate the discovery of life-saving medicines by modeling complex molecules that ordinary computers cannot efficiently simulate. At the same time, physicists continue searching for something even greater, a single theory capable of uniting quantum mechanics with Einstein's theory of relativity. These two extraordinary theories describe nature with incredible accuracy, yet they remain fundamentally incompatible under the most extreme conditions. Inside black holes and during the first moments after the Big Bang, both theories should operate together. Yet their mathematical descriptions refuse to fully agree. Some researchers believe quantum gravity will provide the missing bridge between these two pillars of modern physics. Others investigate string theory, loop quantum gravity, and entirely new mathematical frameworks that may reveal an even deeper layer of reality. No one knows which path will ultimately succeed. History has shown that every great scientific revolution begins with questions that once seemed impossible to answer. Perhaps the next Einstein, Planck, or Schrödinger is alive today, quietly asking a simple question that the rest of the world has overlooked. The universe still guards countless secrets beneath the quantum world. Every experiment uncovers new mysteries, reminding us how much remains unexplored. Quantum mechanics has taught humanity one unforgettable lesson. Reality is not limited by human imagination. The universe is always more surprising, more elegant, and more mysterious than we expect. Our journey through the quantum world ends here, but the search for understanding never truly ends. Every discovery opens another door, inviting the next generation to step forward and explore the unknown.